liverymen and freemen of the Worshipful Company of Engineers, and a special welcome to many guests that we have with us this evening from across the livery movement and indeed beyond. And there are many of you in this, certainly in the advanced bookings, full to capacity Zoominar. Is that actually a word? Zoominar. Yeah, it's a word now. It's a word now. And this is one of a series of lectures and panel discussions under our remit in our charter to promote engineering within the City of London and to help illuminate the contribution that engineering makes to the success of the square mile and beyond. Tonight, topic is achieving net zero, the challenge of delivering zero carbon energy systems. And we're really fortunate this evening to have a speaker and three panelists with deep knowledge of the subject, and it couldn't be more topical. Address to the Conservative Party conference, where he announced new investments and commitment to offshore wind to make the UK world leader in clean wind energy with 40 gigawatts, up from 30 as had originally been planned, 40 gigawatts of offshore wind by 2030. So, is that the problem solved? Boris may well think so. I'm sure our speakers will have more to say about that. We'll begin this evening with liveryman Tony Roulstone. Tony is a member of the Royal Society Study on Energy Storage and a member of the Faculty of Engineering at the University of Cambridge. Much of his career was in nuclear and aerospace and was managing director of Rolls-Royce Nuclear Group. And Tony will speak for about 40 minutes or so, and then I'll introduce three more panelists in turn to give their immediate reactions to Tony's lecture. Tony, could I ask you to kick us off this evening with your first talk? Thank you.
Well, thanks for the opportunity for talking about this. We planned it, I think, started about this time last year, and we were going to give it in the spring, and it's turned out in the autumn. And I thought I had going to missed my point, but as it happens, events sometimes conspire for you rather than against you. Now, net zero as an idea has been around for more than a year. It passed into the UK law in June 2019 as an amendment to the Climate Change Act. So it is the law now. It says we are going to have a net zero economy, net zero in everything by 2050. As we shall see, this target is much more challenging than the previous one. It's tougher. It covers much more of the UK economy. It removes many of the exceptions and opportunities to avoid action. And in the case of Scotland, it brings forward the date, well, at least the proposal is to bring forward the date for Scotland to 2045. Now, as I will argue, net zero provides many opportunities for technology innovation by engineers and for investment by people in the city. And it requires a completely different approach. It's, as some people might think, another ratchet, another step along the road. It requires a completely different approach because net zero rules out things which we thought were possible. It's not just more of the same. Right. So to start, you read the thing yourself. I used to believe global warming was a vast human conspiracy to destroy the polar ice caps in order to get rid of the polar bears, but now I'm not so sure. And we are constantly shown pictures like this, perhaps more pretty than this, of melting ice caps to dramatize climate change, and are told to save the Arctic ice sheet or the Antarctic glaciers. While these points are important, as are the living things that depend on them, it's much more about the changes that are affecting and will affect the rest of the world, not just the ice caps, but the rest of the world. These will have profound, lasting, and potentially catastrophic effects elsewhere, and that's what is energizing action. It is, to use the modern phrase, a climate emergency, not because the effects are occurring now, but because unless we take urgent, far-reaching, and ambitious action now, later when the effects are closer to home, it will be just too late. And we'll wonder why we did not act when there was still time. So, net zero. This was talked about a great deal at the election. And what we've seen, if over the period of perhaps the last 20 years, the arc of UK public opinion change from widespread scepticism at the turn of the century to broader public acceptance, and now to international political support, which, if not uniform, the politicians have accepted that net zero, at least as a target first in Europe, and now net zero by 2060 in China, means that quite large areas of the globe have accepted this sort of idea. And the Extinction Rebellion populist movement, which has been very evident on our streets and with our children in the last couple of years, has had a big effect on public opinion, even if not everyone may like their tactics or their tone. Now, in the 2019 election, all the parties were agreed on the target. Absolutely no difference between the parties in terms of the target and of its importance, even if they did not agree how it is to be achieved. There was a bidding war, I might say, at that time for what it would mean and what it would cost. And some examples which were in the press at the time of the scale of the problem. Labour Party talking about 27 million homes need energy efficiency. Someone else talking in the Telegraph about 4,500 new trains, electric trains, hydrogen trains required. And then also talking about 100 billion for investment. And this billion thing will come up again and again, because this problem is not $1 million problem, it's $1 billion problem. So that I think that there's a lot of public support for this. Whether the change will be made by the government action or by private investment, the numbers, I think we will see, are big. So my contention, having been involved in this working party for the last year, is this is not an incremental change. It's a very much a different change. Net zero is not more the same. It changes everything. The 100% target removes the hiding places for incomplete solutions. We've already done the easiest things this last, and the last 20% from the old target of 80% will be the hardest. It's not just about energy, it's about the whole economy. It's not just about electricity, or it's not just about burning coal, it's about the whole economy. That we will find that buying carbon credits from abroad, which was one of the ways of balancing the equation before, is becoming to be seen as a fudge, and in future, I argue, will become politically impossible. Coal, we've sort of seen the end of coal, almost unimaginable 15 years ago, but coal is either gone or going. It's absolutely tied and done. And more contentiously, I think we can see the end of oil and gas, at least its use without emissions capture. And this is not that far away, not when we talk about the 2050 timescales. And two of the biggest companies on the FTSE, Shell and BP, are starting to face up to this and realize this is a big change. And when we talk about the timescales, people want us to act on the timescales of 10 or 15 years. 30 years is not long to act when you get down to it and consider what needs to be developed that's new, what needs to be proven before it's deployed, the scale, the range and cost of the deployment, because it's across the whole economy, and what will be required to change people's behavior. So let's just look at the nature of the problem. That few facts and figures, we've made much progress. The greenhouse gas emissions, this is all the emissions, but put in terms of million tons of CO2 equivalent, have been reduced by about 44% since 1990, when we started counting these things, from about 800 million tons to the current 450 million tons. The old target was an 80% reduction, about 120 million tons of CO2 equivalent. The new target is net zero. That means either no emissions, or where there are emissions, having countervailing emission removal, where you have negative emissions to balance this off. So this is a really tough target. There's no margin, there's no bit at the edge. It means zero, and for anything that's left, some negatives. So let's just look at some of the sectors. The largest sector in this thing, in terms of emissions, is transport, which is cars and lorries and planes and ships and trains. This is the largest, and when people say we'll fix this with electric vehicles, there's a little bit more than electric vehicles to fix. The next largest is energy, which these days is mainly gas. Huge, still about 50% of our electricity is from gas, and this merely emits CO2. Industry, very important area, because some of the most difficult problems are in industry. Some of the process industries are quite difficult. And here's a picture of a cement making process. Quite a difficult area to fix. There's all the electricity we use domestically and the gas we use domestically and in commercial buildings. These two together add up a very large amount. It's important, not just electricity, but the heat that's involved in those. And then let's not forget agriculture. Agriculture has emissions as the famous methane from from cows, but also fertilizer, and also tractors and transport and heating and all the processing that goes with it. So agriculture is also a big affair. So the net zero applies to all those. It's not just about electricity. It's a very big subject. Luckily, we have some solutions at hand. It's not all doom and gloom. We have a palette of technologies available that, for much talked about, that the hydrogen as a possible carrier of energy, which can be made by electrolysis, splitting water, or by steam methane reforming, which is effectively the same, splitting methane. So there's large-scale industrial process which is possible. There's renewables, talked about today, solar and wind, and probably energy storage, and nuclear is another clean energy source. That for heating, the issues of heat pumps need to be thought about, and gas boilers, perhaps with replacing gas boilers or gas boilers with hydrogen. And then for transport, the famous electric vehicles. And then what are we going to do for trucks and trains? And the people advocate we should have hydrogen trains or hydrogen trucks or electric, either of those. So this will progressively affect a large area of the economy. So what do we expect 2050 to look like? First of all, there will be energy efficiency measures, be widespread and are successful. We need power, all of our power, from clean sources. Natural gas will be replaced by hydrogen or heat pumps. Surface transport will become either hydrogen or electricity. Ships will be powered by ammonia or hydrogen, and bio or synthetic fuels for aviation. And CCS will become important for specific industrial processes. This is too big a topic to talk about this evening, but I want to talk about three, what I call strategic challenges, where there are quite big questions that need to be answered, and the future is not quite certain, and they need some evolution, and some decision making. They're important issues. The first one is about heating and hydrogen. The second one is about the role of carbon capture and storage. And the third one is how do we keep the grid reliable with lots of renewables. So I'm going to go through each of these in turn and talk briefly about them. So first of all, heating and hydrogen. Hydrogen is a front runner, both for heating and for transport, to replace oil and gas. The question is, how much of it do we need? We know it's a flexible energy carrier. It needs to be made. This requires energy, and it needs to be transported. Now, potentially, we can make use of the gas grid, where this is plastic lined, but it will require some changes to the local infrastructure, which is not all plastic, and definitely into the houses, which is not a plastic, and then changes to appliances where it is burned. This means digging up many, many roads. It means changing tens of millions of homes and offices. But it looks that this is a feasible thing to think about. The current UK hydrogen production is about 27 terawatt hours. These are, we usually talk about kilowatt hours or maybe megawatt hours. Electricity bills are in megawatt hours. This is 1,000 megawatt hours is a gigawatt hour, and 1,000 gigawatt hours is a terawatt hour. So we're talking about a million watt hours. So the currently we make quite a lot of this industrial process by steam methane reforming, mainly on the Teesside on the old ICI place. So this graphic, which is from the Climate Change Committee report in the autumn of last year, says, well, how much energy hydrogen do we require? They said, well, we can imagine a niche hydrogen approach, which by 2050 might grow by a factor of 3, or hybrid hydrogen, where we use hydrogen in some places, but not across the board for heating, or a full hydrogen, which is 25 times. So there's quite a big range in this between a little bit more than the 27 terawatt hours, or huge amounts more. And this is an open question at the moment. And then if we are going to produce all this thing, how will it be produced? And will it be the best choice for heating? A rather complicated slide here, but I think this intends to make a point. There are basically 3. Heating is the biggest use of energy. In the future, it'll probably be about 600 terawatt hours, half the total energy at use. It's a big number, and it's a big carbon producer at the moment because it's nearly all natural gas. So how do we do the heating job? Well, there are 3 choices. The so-called blue hydrogen, there's green hydrogen, and there's heat pumps. So if I just briefly go through each of those. So blue hydrogen is taking natural gas, breaking it down in a methane reformer, heating the natural gas up, injecting steam at several hundred degrees centigrade with a catalyst, and it breaks down to CO2 and hydrogen. It's about 70% efficient. We know it works, and we know how to do it. It can be supplied through the gas grid. It can be used for transport power, but needs some cleanup because, particularly for fuel cells in transport, they don't like methane. But it does require carbon capture and storage, because otherwise you have exactly the same CO2 emissions as you would if you burnt it in the house. And it's got some issues with carbon intensity. It's what I would call mid-cost. Now, all these technologies are significantly more expensive than just burning natural gas. They're all about at least twice the price. And this is the cheapest of the 3, 2.5 times what the price of natural gas is. This is using figures that Bayes have produced. The second approach is to use electricity. And electricity can be from windmills or from solar or from other clean sources like nuclear or BECCS. And you go through an electrolysis process, and you get about 70% of the electricity that goes in comes out as hydrogen, green hydrogen, pure hydrogen, and it can again be distributed through the gas grid. It can be used directly in transport, but it does imply a much larger electricity system to produce this huge amount of energy. It is somewhat higher cost than blue hydrogen, and though people say they see the price of green hydrogen coming down, some of the basic fundamental facts, which is that it starts from a high quality and therefore relatively expensive form of energy, electricity, which you're then turning into heat, having turned it first into hydrogen. So this is doing the opposite of what engineers do, who like to turn heat into electricity. This is turning electricity into hydrogen into heat. So it's always going to be higher cost, and probably more than 3 times what the cost of gas heating is now. The third approach is to use electricity again, but to use it in a different way in heat pumps. These are things like the air conditioners we have in our buildings, or a reverse fridge, you might think about it, which takes what is cold heat from outside, raises its temperature and brings it into the building. And the good thing about this thing is it uses electricity, but it actually produces as an output where you want it 2 or 3 times as much heat as you put into the system. And therefore it has a sort of an efficiency of about 250%. So it looks like what the engineers would like. It could be put into replacing domestic boilers or put into individual rooms. It has a problem about not being very effective when the temperatures are very low, but it does require a somewhat larger electricity system than we have at the moment. But again, because it uses high quality energy as electricity to produce things, it can be high. And also because this electricity is generally retail electricity, it will look quite expensive rather than other things where the energy is wholesale. Now, the real question is, there's these three ways of doing it. I don't think there's anything novel in this. People will agree these three ways of doing it, but we do need to decide because it has an effect on the infrastructure. Are we going to dig up the roads to put new cables in? Or are we going to remove all our substations to put more power into houses? Or are we going to dig up the roads to put new hydrogen pipes in? Are we going to do both of these things? And who's going to invest in all these infrastructure changes unless there's some clarity about what the right solution is? So that's the first thing to be thought about. Secondly, carbon capture and storage. Again, people talk about this and are very enthusiastic about it, quite rightly, but it has its problems. So I think net zero, achieving net zero, will depend on having carbon capture and storage. Perhaps not in the way that many people think about it. It will definitely be required to remove and balance difficult greenhouse gas emissions. The graphic here shows the general form of it, that in this case, what we call post-combustion, so you have CO2 in the output of some power plant or industrial plant in the flue gas. It's then captured by some process, some reversible process, which captures the CO2. The CO2 is then stripped up from the reagent that captures it, pumped up to high pressure, transferred and stored underground. It's a well understood process. It's not a new process. However, it's got quite a number of steps. There are basically three main applications for carbon capture and storage. There's direct air capture, which is taking the 400 parts per million we have in the air and capturing it and putting that underground. This is directly acting on the past history of climate change. There's bioenergy carbon capture. This is burning a natural fuel which has already got carbon that's been grown in naturally, which is captured from the atmosphere. They're called BECCS. And there's carbon capture for normal energy back on the back of gas turbines, on the back of steam methane reformers. And the real question is, will it be used for these later use, making hydrogen for gas or cleaning up the natural gas power? Now, in the UK, we have a slightly tortured history with CCS. But we've tried, some projects have started and stopped and started and stopped. But there are some examples of this around the world. There's about 22 large CCS projects. They're mostly, and this is a picture of one in Texas, Petronova. It's on the back of a coal-fired power station. And they've got the wonderful ways of having captured the CO2. They put it back into the ground, into oil wells to drive out more oil. So it's called enhanced oil recovery. And therefore, this looks economic because it's a backfit of a plant and it produces more oil. But it's not really a net zero technology because we wouldn't be burning coal in the first place. And secondly, we don't want to get more oil out of the ground. That many more are being planned in a number of countries. And the current performance of these plants is they get about 85 or 90% of the carbon dioxide out of the plant. There's theoretical possibility of getting some more, and with a completely different process of capturing it before you burn it, such as the alum process, you can perhaps get as much as 100%. But the main issues for carbon capture and storage are cost and residual emissions, as you might expect. So currently the cost of adding CCS to a gas turbine is it puts the energy cost up by about 50%. And it's slightly more if you're talking about the alum cycle. But importantly, if you put CCS on a bio plant such as the Drax, which burns wood pellets, the cost has been estimated by Bayes again to be very much higher, perhaps 300% more than this. So that's a cost problem. They have a cost problem. Now to perhaps explain the other one, the residual emissions. They come in two parts, but here's a nice little graphic from the Climate Change Committee. So on the left, we have This is using CCS associated with producing hydrogen with steam methane reforming. And on the left, you have the intensity of natural gas. And if you do no CCS, it produces about 200 grams of CO2 per kilowatt hour. And then there's a funny box on the top, and that is what they call the upstream emissions. They're mainly methane, but methane has a very strong global warming effect, and the small emissions of the methane push that up to about 250. If you put carbon capture in this system, it will bring down the process emissions to figures like 25 or 50 grams per kilowatt hour. So it's a big change, but those upstream emissions then become key. These residual emissions are the Achilles heel in a system where, because there are other hard emissions in the economy, the energy process will have to be zero carbon. And studies have shown that if we want net zero, it's only feasible if we completely eradicate these upstream emissions and we get to 99% carbon capture. And that's not currently where the technology is. So thirdly, windmills and solar. So on the basis that 2050 electricity supply is completely carbon free, we can see why the government has made its aim for the UK to be the Saudi Arabia of wind. We have natural wind resources, we have plenty of wind resources, and it is, at least at the point of production, carbon free. And also the falling prices of wind and solar over the last 10 years mean that it's highly investable, it's becoming cheaper and cheaper, and it will become the dominant means of supply just because of market forces. And it seems that to meet the demand for energy in 2050, we'll go from about it being 20% of the current energy demand to about 2/3 of the larger energy demand which might be present then. This actually is probably a 7-fold increase. And instead of the figures like the current target was 30 gigawatts wind going up to 40 gigawatts announced by Boris today, actually we'll probably need about 100 gigawatts of wind and 100 gigawatts of solar to meet 2/3 of the power requirement then. But these are promising technologies. We have demonstrated them at scale. That there are some challenges in those. We know demand varies. We know supply varies because it's weather dependent. We've got the issue of lack of coincidence in time of supply and demand, and the issues of grid stability to do with what's going to stabilize this system. These are largely going to be replaced or may turn out to be inadequate. For short term, we currently have spinning reserve of turbines, CCGT and nuclear turbines. If we're not going to have gas and gas turbines, that spinning reserve will go. We have a dispatchable capacity market to fill the gaps on a longer time. If you look, nearly all the dispatchable capacity market is fossil fuels, old coal-fired power stations, diesels, some gas turbines and such like. I don't think that those things are going to be there. We will still have hydro and storage, but it's quite limited in size. As we'll see, a figure of 27 gigawatt hours is quite small by the need of the future. The largest energy store we have in the UK, which will still be there, is the current bioenergy store for Drax, which is about 400 gigawatts when it's expressed as electricity. We have currently 55,000 gigawatt hours, 55 terawatt hours, a very big number of gas storage. But if we're not going to burn gas for energy, then this will not be part of the system. And people say, well, what about electric vehicles? If we make use of a portion of the energy for all the electric vehicles in 2050, it's about 1,000 gigawatt hours. I don't think this is going to be enough. So I just want to deal with these two issues of mismatch of time and the business about the weather. It's a chart which we produced as part of this Royal Society work, and it's quite instructive because it's not a problem we can avoid. So for this, if we say that the demand is about, on average for the year, about 600 terawatt hours, which is a central assumption, we know that this varies day to day, and it varies week to week and month to month and season to season. And if we have a wholly or largely renewable energy system, we know the characteristics of it will mean that sometimes that there won't be enough demand to absorb the supply, and therefore there'll be energy wasted. And at other times, there'll not be enough supply to meet the demand, and therefore there'll be a gap. And what we find is, just because of mistiming, that if a demand of 600 terawatt hours, if the supply is less than about 300, nearly all the energy is absorbed. But as one gets towards the 600 gigawatt hours, the curve turns over. And although you have nominally 600 terawatt hours of supply and 600 terawatt hours of demand, because of the mistiming, you're short of about something over 100 terawatt hours in the year. So this mistiming effect is important. And people say, well, we'll just solve that by having a bit more supply and waste it. But actually, because the curve turns over, you need to go up to perhaps 3 times the nominal demand at great cost. Or you have to have some dispatchable complementary supply, the thing that gas turbines do at the moment. And so there's an issue of what do we do about to fill this gap? And their options are maybe CCGT with CCS, nuclear, energy storage and BECCS. And what we've been looking at is energy storage with some features. So just to go on to energy storage. Now, people, when they talk about energy storage, and I read in the paper, they equate this with batteries. You know the price of batteries are coming down. So if it's all batteries and the price of batteries coming down, the problems will solve itself. Well, it's not all batteries. Energy storage has a number of technologies, and that's the review we've been doing to look at the scale of the need and the duration of storage and the type of technologies that are required. And really, there are 3 different types of technologies. There's electrochemical, which are batteries, either static batteries like Li-ion batteries or flow batteries. And here we see the largest battery in the world. This is the Tesla battery in South Australia at Hornsdale, 150 megawatt hours of Li-ion battery, stabilizing the grid in South Australia. And everybody's very proud of that. Installed in about a year, a great success, but it's relatively small. Then for bigger stores, we have things which depend on physical principles, generally compressed air or liquid air or thermal energy. And there are a couple of large plants in the world, one at McIntosh in the USA and the state of Alabama, using compressed air, and there's another one in Germany at Huntorf. And they have demonstrated that storing high pressure gas at about 80 bars in salt caverns well below the earth is a good way of storing energy. These things have worked well for a while. And then for the longer term, the idea of using hydrogen chemical bonds is a much denser form of energy, and either directly as hydrogen or perhaps as ammonia. The idea is you take solar energy, you turn it into hydrogen with an electrolyzer, you pump it again at high pressure, perhaps 80 or 100 bars underground, these salt caverns, and then you let this out when you want some energy, either through a fuel cell or a gas turbine or maybe even a reciprocating engine to produce your power. Now, what we see is there's some differences between these things, and some in the specific costs, capital costs here. And what we see is, first of all, the range of difference in this is effective volume, the storage cost, the effect between 160 and 0.14. That's 1,000 times range of different cost. And for power, they go from 36 pounds per kilowatt of power from electric up to something over 1,000, about 40 times. So there's huge differences in the specific cost of storing energy or power from energy. And luckily they go in opposition. And so some things will be suitable for short periods of time where you want high power, but you're not storing much energy. And other things where the amount of energy you store is large, but the power requirement is less. And we notice also the efficiency, the round-trip efficiencies of these systems is different. Batteries with their inverters is generally quite efficient. The physical systems are a bit less efficient. Compressed air systems, perhaps 50%. And there's some ideas about advanced adiabatic Ks at 70%. And the chemical ones, because of the number of steps they go through, making one to the other, they tend to be lower in efficiency intrinsically. Hydrogen at about 40%, and that's quite a good figure for hydrogen. and ammonia down at 25%. So what we see is no one storage technology can fill the whole of the need. And therefore, we need to think about how do we design a energy storage system. So I think for the first time, we've been doing this work looking at many years of weather. We've looked at 37 years of weather and a number of stores working together in finding out how to minimize the size of the storage and how to make it most economic. What we find is if you just have a simple store to fill that compensating gas, it's huge in its requirement, 238 terawatt hours, which is about 100 times all the energy you could store and make available in electric vehicles in 2050. This is just an unmanageable amount of energy in batteries. Luckily, we find that a small amount of overcapacity in the wind system at least halves this thing. It brings it down to about 90, 98, something less than 100 terawatt hours. However, we put efficiencies into these three store systems. We need larger amounts of overcapacity to balance it, but we can get down to about 60 terawatt hours with 30% overcapacity. And there are scope for further reductions by having some base load of something else like nuclear or BECCS, and also the effect of interconnectors with the rest of Europe has an effect. But what we see is quite clearly from the data is there are three different types of needs. There's a short need of about a day to cover the variations in demand during the day and the variations particularly in solar. And this has a size of about 100 or 200 gigawatt hours and that store operates at 30 or 100 times a year. There's a period, a long period where very large amounts of energy is required to be stored, but this store cycles very seldom, sometimes less than once a year. And in between, there's a period of from a week to several weeks where you get this very random wind-driven weather which comes across from the North Atlantic and requires quite substantial, a couple of terawatt hours of storage. And again, it cycles very little. One of the things I think this has made clear is that we need different types of store for different types of needs, but also the case for making these stores what we call merchant investments, where someone will set up and say, I've got a medium store and I will buy and sell energy. It just doesn't work because of the small amount of energy that's supplied and the number of cycles that run are small, and therefore it just is uneconomic, and it does not seem conceivable it will be economic. However, these are the things that are required to balance the grid. So it says that these investments probably would be better be grid scheduled and perhaps grid owned, even if the underlying investment was private, because merchant type of approach will either not meet the need because it'll operate when not required, or it'll have so little revenues that it won't be effective. So what does all this have effect on energy cost? And again, this is what we've been doing. When people comparing technologies, they very often talk about the levelized cost of electricity, the levelized cost of electricity of CCGT or nuclear or this technology or that technology. What we say is for a renewable system which needs storage, if we put all these things together, we get what we call a blended energy cost, the renewable cost, the overcapacity cost, and the storage cost. And we work out the levelized cost of all these things. Now, for this modeling, we've not used any random figures. We've used absolutely standard figures. We use figures for the cost of renewables to be 2040 from the International Energy Agency. And when you blend these things together, they have an average price, a future price of about £50 per megawatt hour. This is the green line. We used for renewable energy costs, for storage costs, those that produced by the Renewable Energy Association, ARENA, again published. And the problem about those is they're quite the wide range of because they're not as well studied and not characterized and built as others. But what we see in this graph is the base cost of this system is the renewable energy, and then as it's plotted against overcapacity. If you have a bit more overcapacity, it goes up. But putting more overcapacity makes the stores smaller and should make the cost lower, but actually it perhaps doesn't. What we see here is that taking the mean costs, unit costs out of the system, that as it's first modeled, these stores do not share power very well, and therefore they all need to compensate for the huge variations in power, the residual power, which might be 100 gigawatts. So you need 100 gigawatts that's going to be used infrequently and has to stand by in order to be able to provide this power. That makes it very inefficient. So if we can share power between these stores, we get a much better result. And this is clearly where we've got to. And then if you took the most optimistic costs that are given in the literature, which are not really supported by any evidence, but are sort of part of trends, you could get figures down much lower. But what we can see from this very early analysis, that the blended energy cost for a big renewable system is perhaps twice the level of the base renewable cost. And the lowest energy costs are actually associated, at least in this analysis, with the lowest level of overcapacity. But these preliminary estimates are very sensitive to the cases and the modeling. Not much of, I think we're the only people who've done this in the UK anyhow, to do with how power is scheduled, what the future costs of storage will be, and the availability of flexible and zero carbon energy. We have also found that bringing some base load in, it does reduce the overall cost of energy. And so on the side, we show up here some examples. BECCS is rather expensive. It's more expensive than this combined renewable energy. Nuclear looks like it could well be lower, and therefore having a nuclear component will reduce the overall system cost. So getting towards the end, or getting to the end, I think I've argued, and I'm pretty convinced, net zero changes everything. It's not just more of the same. It's going to change the energy industry, and it will affect the whole economy. It'll get into areas that we have not really thought about. There are some major developments and some major decisions to be made. We've got to decide for heating whether we can use hydrants or heat pumps or what combination. We have to decide something about CCS, whether to use it for energy or not. It will be used for industry, for things like cement and steel and glass making, where there's almost no alternative. We will have a highly renewable system, but what is it going to look like? And is it going to have energy storage, and how much base load does it want? But what we do know is the scale of change is unprecedented, and it would lead to a novel design of systems. The energy investments were massive. You may have noticed figures as I was going through, but if you start and add these things up, the investment is huge. You have to invest in renewable energy supply. We're talking about 100 gigawatts of wind and 100 gigawatts of solar. For CCS in industry, biomass and DACs, direct air capture, it's expensive but probably required. For base load, perhaps nuclear. How much nuclear do you want, and are you going to have it operating as flexible supply? And do you want large reactors or small reactors? For energy storage systems, again, they can be extremely expensive. We need to expand the grid and the charging infrastructure. So the decisions we have to make have got uncertainties, and we'll need more work on feasibility and optimization. And they will have far-reaching effects, but the decisions on these matters actually are quite urgent to be able to deliver on a net zero timescale by 2050. It's going to take a lot of money. Now, is this, I think it's about $1 trillion. Is this $1 trillion problem, or is it $1 trillion opportunity? I'll leave it to you.